Okay, so what did we do last time again? Mean value theorem. Mean value theorem is good for what? Well, we were able to prove a few technical things that without it, we would be in trouble trying to prove. For example, we said in the end of the class that if two functions have the same derivatives, right, the derivative of f is equal to the derivative of g, then they have to be essentially the same except by a constant. One of them is a constant plus the other. Okay? And that is something that would be very hard to prove, actually prove, even though it's obvious, except that using the mean value theorem we can do it. Okay? Today, we will continue to use the derivative of a function to find out how a function looks like. Okay? And the idea is to find out what f prime and what f prime prime tells us about the graph of the function f. So this is 4.3. What f prime and f prime prime say about the graph of f. Okay, we're going to break this down into two parts. The first part is what f prime says about f. And then we'll talk about what f prime prime says about f. Okay, so we're going to focus on very broad qualitative features. For example, what happens if I know that the derivative of a function is bigger than 0? Exactly, the slope of the function f is positive, right? So you can imagine the slope always being like this. So what can we say about the actual function f? It's an increasing function, right? Everybody agrees? Yeah. All right, so that means that f is an increasing function. And if f prime is negative, that means that f is decreasing. Let me draw this in an example, in a cartoon example, just to make sure we're all on the same page. So we have a function, let's say, like this. We're going to break this down into three intervals. One is from here to here. Another one is from here to here. And the third interval. And on this first interval, right here, in this region here, f prime is bigger than 0. On this second region here, f prime is less than 0. And on this third region, f prime is bigger than 0. Well, you can see that very easily, because if you drew the tangent line anywhere in here, you would have a positive slope, negative slope, and here a positive slope again. But what that means about the function itself, about the function f, is that f is increasing. But over here in this interval, f is decreasing. And over here, f is increasing again. All right, so if you agree with me on this graph, I think we're all on the same page. Fairly straightforward statement to make about the function f. Let me give you an example. F of x equals 2x to the 3 minus 3x to the 2 minus 12x plus 1. And the question is, find where f is increasing or decreasing? Okay. So we want to find where the function is increasing or decreasing, and because of this information we have here, we want to find is find where f prime is positive or negative. We first compute the function f prime. F prime is equal to, derivative of this thing is 6x to the 2 minus 6x minus 12. I can conveniently factor the 6 out, and this is 6 times x squared minus x minus 2. Okay, and now I would like to ask you guys, how do I factor this out? So, those of you who haven't been in a middle school for a while, is it in middle school you learned this? High school? All right. So you're looking for two numbers whose product is minus 2 and whose sum is minus 1. Okay? What will be those two numbers, let's say? I don't know. Anybody wants to say? What are two numbers that are product is, what is it?
X minus 2 plus 1.
Yes, thank you. So, minus 2 and plus 1. Great. So the number minus 2 and the number plus 1 are such that the product is minus 2 and the sum is minus 1. Great. Be it as it may, you can factor this out, and now we can look at where this function is positive and where the function is negative. What we're going to do is first find out where f prime is equal to 0. Okay? If we want to find where it's positive and where it's negative, let's start with finding where it's actually equal to 0. Where is it actually equal to 0? Where at x equals not plus 1 but minus 1, and where x equals plus 2. Do you agree?
Yes.
Those are the points where the function is actually equal to 0. So what we're going to do is we're going to break down the real line into a bunch of intervals. One interval is the interval x less than minus 1. Okay? Then another one is the interval between minus 1 and 2. And the other one is where x is bigger than 2. Why am I doing this? Well, let's imagine that the real line is right here. And I know that this function, the derivative, is equal to 0 at this point and this point. So that means that inside this in between is not going to be negative. I'm sorry, it's not going to be 0. It has to be either positive or negative. Okay? And over in this interval, same thing. The function has to be either positive or negative. It can't be 0 because the only points where it's 0 is here and here. All right, so let's first start with the function 6 x minus 2. Okay, so the function 6x minus 2, is it positive or negative in this interval right here?
Negative.
It's negative, that's right. In this interval right here, think about any number between minus 1 and 2. Let's say x equals 0. So that would be here negative, right? So think about any number between minus 1 and between minus 1 and 2 and plug it in here to see if it's positive or negative. And now let's take any number that is bigger than 2, plug it in here, it's positive. That's right. Now let's take x plus 1. And let's say over here, a number that's less than minus 1, we plug it in here, gives us negative. What number would you choose? Well, let's take the number x equals minus 5, let's say. Minus 5 plus 1 is minus 4. It's still negative, right? So it's negative. Any number between minus 1 and 2, this expression is positive. And over here it's positive 2. Okay, so now knowing the sign of each of these things, we can put all together and multiply 6 times x minus 2 times x plus 1. And this is now the product of a negative number and a negative number is positive. This one and this one is negative, and this one and this one is positive. Great. So that way we know when this function is positive, negative, or positive. So that means that because this is f prime, okay, that means from what we were saying that in this interval, f is increasing or decreasing? In this interval, f is decreasing, and in this interval, f is increasing. Great. Okay, so that's the first part. That's really the basic information you can get if you know the derivative of the function. You just look at when it's positive and when it's negative. Okay, now remember what we did in the previous lecture, before the last one? We have been talking about maxima and minima for a while, right? So we're trying to determine when a function has a maximum and when it has a minimum. And we already said, you evaluate the function at each of those critical points, and the maximum value of those is the absolute max, and the smallest one of those is the absolute min. But we would still like to know a little more. I think somebody else was asking me, what do we know about those intermediate values, right? If it's not the absolute maximum and it's not the absolute minimum, how does it look like? Is it a local maximum? Is it a local minimum? Something in between, okay? So the derivative function, especially knowing the signs, we can find out information about whether a point is a maximum or a minimum, a local maximum or a local minimum. So once again, in summary, what we did before could help us to find the absolute maxima and minima. Now we can find out about the local maxima and minima. What do you think? This is actually a fairly straightforward thing once you realize it. If you know that a function is increasing anywhere less than -1, and you know that the function is increasing anywhere bigger than -1, what must happen at -1? Okay. Once again, I know the function is increasing on this side and is decreasing on this side. So what must happen at -1? It's not increasing or decreasing, right? Okay, but what more?
It's a point of inflection.
No, it's not a point of inflection. Okay, once again, it's increasing. The function is increasing at x less than -1, and it's decreasing at x bigger than -1. This is x equals -1. Can you see that? It's a little hard to see. Okay, but there we go. So the function is increasing in this interval, and it's decreasing in this interval. So what must happen at that point? It's a local maximum. Okay? All right, so there you go. So this brings us to what's called the first derivative test. So this information helps find local maxima and minima. We can form what's called the first derivative test, which says the following. If f prime changes from positive to negative at C, then C is what? A local maximum. Like this. If f prime changes from negative to positive at C, then C is a local minimum, because you see it goes from negative to positive. And C is, the part C is if f prime doesn't change sign and f prime of C is equal to 0, it is not a max or a min. So for example, this could be a situation where the derivative is positive, then it goes to 0, and then it's positive again. So you see this point is a point where the first derivative is 0, and yet it is not a maximum or a minimum. Okay? Now this first derivative test is usually done with points that are critical points. So for example, let's write this down as an assumption. F prime of C is equal to 0. Okay? So suppose you have a point that is a critical point, say that f prime of C is equal to 0, and you're thinking, well, is this point a local maximum, local minimum? What is it? So one idea is to look at the first derivative. This is why it's called the first derivative test. Is it going from positive to negative? Then it has to be a local maximum. Is it going from negative to positive? Right? Okay, great. All right, so a couple of notes. Well, okay, one note. One note. The first derivative test works even when the function is not differentiable at C. For example, you can look at the function absolute value of x. Okay? Absolute value of x looks like this. You look at the point 0, the derivative goes from negative to positive. Right? So you can tell from the first derivative test, you can tell that the function has a local minimum at that point because it goes from negative to positive. It doesn't actually matter that the derivative doesn't exist at 0. That's already a point, something that goes beyond what we were doing. Okay, even if f prime of C does not exist. Okay. Oh, I see what's going on. Sorry. Better? Okay. All right. So now let's apply this first derivative test to the example before. Once again, f of x is equal to 2x to the 3 minus 3x squared minus 12x plus 1. F prime of x is 6x squared minus 6x minus 12. And we said that between for x less than minus 1, this thing is negative. Sorry, actually positive. For minus 1 less than x less than 2, this thing is negative. And for 2 less than x, this is positive. So that means that at x equals minus 1, f prime goes from positive to negative. So it's a local minimum or a local maximum? Okay, it goes from positive to negative, so local max. Okay. At x equals to 2, f prime is negative to positive. It's a local minimum. All right, that's it. Good, so now we can think about what, let's see. Actually, let me take another page here. Let's think about what f prime prime says about the function f. Okay, so what do you think? If the function f prime prime is positive, what can we say about the function f? Actually, let me keep this here for a moment. What f prime prime says about f. Okay. So if f prime prime is bigger than 0, then I still don't know what happens with f, but I know that f prime has to be increasing, because you see f prime prime is a derivative of f prime, right? Then f prime is increasing. Okay, so if f prime is increasing, that means that the slope of f has to be increasing. For example, if it starts here, then it has to be here, then here, then here, right? So what do I know about f? Well, I know that the slope must be increasing. So for example, if the slope was 0 here, it has to be 1 a little bit later, or 2 or something like that. The slope is increasing. So what does that say about f? It means that the function, no, it does not say that the function is increasing. It means that the function f is curved up. That's what it says. Okay? So whatever it is the slope is increasing, so the function is curved up like this. Sometimes I hear that described as a happy face. Okay? So no matter what the function is doing, it has to be curved up like this. For example, it could also be, it could also look like this. You see over here the derivative is minus 2, let's say. Over here the derivative is minus 1. Over here the derivative is 0. It's the same story actually. The derivative is increasing. Even though it's negative, it's still increasing. So it still has the same curvature. Okay? So we call this thing concave up. Concave up. Or happy face. All right. Okay. So if f prime prime is negative, then f prime must be decreasing. Right? Because f prime, the derivative of this is this, so by the previous argument, this function must be decreasing. That means that the function is concave down. Concave down or sad face. Okay? Down like this. All right. So let me give you a few examples. let's just drill this up. If a function looks like, let's see, suppose that a function looks like this. I haven't shown this one to you first. So let's think about the first. So this is the function f, okay? What is the sign of the function f prime? Is it positive or negative?
Negative.
Negative. How do you know it's negative? Because it's decreasing. That's right. What about the second derivative? Is it concave up or concave down? It's concave down. So that the second derivative is negative. Let's do this one. If this is what f looks like, then I know that f prime is positive or negative? Positive, because it's increasing, right? What about the second derivative? It's still a sad phase, right? Okay, so it's negative. So you see the two things are not completely related. You know, you can have one positive, the other one negative. That's fine. So by finding out the sign of each of these things, you can tell about first whether it's increasing or decreasing, and second whether it's concave up, happy face, or sad face. All right. Is there any question on this? I realize this is a little bit harder than the first one. So is there still some doubt about why the happy face and the sad face thing? You want me to say it again? No? You can look at the video, right? All right. Okay, so, well, there you go. So let's go back to the first example that we were saying before. The same example as before. And the example, f prime is equal to 6x squared minus 6x minus 12. Okay, so f prime prime is equal to 12x minus 6. Now, when is, so this is 6 times 12, sorry, then 2x minus 1. Okay, so when is f prime prime equal to 0? That means that 12x minus 6 is equal to 0, or that 12x is equal to 6, or x is equal to 1/2. All right, great. All right. So let's see. So we write x less than 1/2 and x bigger than 1/2 and f prime prime of x here. And what do we have? When x is less than 1/2, what do you think? This expression is positive or negative?
Negative.
So let's plug any number that is less than 1/2, for example 0, right? And you test whether this expression is positive or negative, and it's negative because 12 times 0 minus 6 is minus 6 is negative. And let's take any number bigger than 1/2, for example 1, right? And 12 minus 6 is 6, which is positive. And what that means is that f is concave down or up? Down. And over here f is concave up. Great. All right. There is actually some more information we can get about about the local maxima and minima if the function has a second derivative that you know the signs of. Finding local minima and maxima. We can write what's called the second derivative test. Okay, what does the second derivative test say? It says two parts. If f prime of c is equal to 0 and f prime prime of c is bigger than 0, so let's think about it. The function has a horizontal tangent at that point. It's a critical point. And it has a second derivative bigger than 0. So it must be happy face or sad face? Happy face. Okay. So it means that it looks like this, right? Is that a local maximum or a local minimum? Local minimum. That's right. Okay, and B says if f prime of c is equal to 0 and f prime prime of c is less than 0, then c is a local max. Why is that? Well, it's because the function has a horizontal tangent at the point, but it's a sad face, so it has to be a maximum. This one, it looks a little funny because here it's the derivative is bigger than 0, but it's a minimum, right? It's a little bit counterintuitive. But it becomes intuitive when you think about second derivatives in terms of happy face and sad face. So negative means sad face means that it's a local maximum. Negative derivative means happy face means that it's a local, the other way around. So bigger than 0 means happy face minimum. Less than 0 means that it's a local maximum because it's sad face. Okay, all right. So now we can try and put all together and find out what the function looks like. Oh, shoot. Back to example. F of x equals 2x to the 3 minus 3x squared minus 12x plus 1. Okay, let's evaluate the function at the maxima and minima, the local maxima and the local minima. For example, f of minus 1 is equal to what? 2 times minus 1 to the 3 minus 3 times minus 1 squared minus 12 times minus 1 plus 1. This is equal to minus 2 minus 3 plus 12 plus 1 is equal to, let's see, so 5, 8. Okay, what about f evaluated at the point 2? Well, it's 2 times 2 to the 3 minus 3 times 2 squared minus 12 times 2 plus 1 is equal to 2 times 8 is 16 minus 3 times 4 is 12, minus 24 plus 1. And this is, let's see, so this is 4, minus 24 is minus 20, minus 20, plus 1 is minus 19. Okay, so 16 minus 12 is 4. Yeah, okay, sounds good. Okay. All right, I'm not gonna go all the way down here to draw it. So I'm gonna be a little bit liberal with the graph. This is minus 1, 1, 2. I'm gonna go and draw 8 over here. And I'm gonna draw minus 19 down here. Okay, so the function must go through these 2 points. What else did we say about the function? From the first derivative test, we said actually over here that the function has a local maximum at minus 1. Local maximum. Okay, and it has a local minimum at 2. So it looks something like this. Okay. We also said that the function is increasing anywhere before minus 1, then it's decreasing, then it's increasing again. All right. So we can try and plot this thing. Well, what is f of 0? Let's see. F of 0 is equal to 1. Which is somewhere down here. And then it starts going back up. Great. Now, this is consistent with the story we had for the derivative, for the first derivative. What about the second derivative? The second derivative we said was negative all the way up to 1/2 and positive beyond 1/2. Okay, so over here in this region here, f prime prime is less than 0, sad face, and over here f prime prime is bigger than 0, or happy face. Okay, this point over here, the point 1/2, has a name. Kendrick was mentioning it a moment ago. It's a point where the concavity changes from one thing to the other. In this case, from sad face to happy face. And this thing is called an inflection point. Inflection with an X or with a CT? Inflection. Inflection point. There you go. All right. Questions? Does that go in the exam? Well, yeah. It's a hard question to ask because we spent a lot of the time of the lecture talking about just one example, as you can see. There's a lot of things you can say about this one function. You take the derivative, you evaluate when the derivative is negative, when it's positive. That tells you when the function is increasing and when it's decreasing, right? Then you take the second derivative and you test when that thing is positive or negative. That tells you when the function is concave up or concave down, all right? And then you put all the information together. If you make any mistake anywhere, then it gets messy because it's not going to all fit together. There's going to be some contradiction. You know, you would expect things to work out and they don't. Okay, so you do have to be extra careful with this kind of problem if you want to use the information of the derivatives to calculate the graph of the function. Okay, we have a few minutes left. This is really all I wanted to say about this section. So let's go back and say something about the mean value theorem. Okay, so in particular, I would like to prove the mean value theorem, if I can. So proof and the first step of the proof is something called Rolle's theorem. Which says the following. Suppose that f is continuous on the interval AB and f is differentiable on AB, and suppose that f of A is equal to f of B. Okay, so we have a point, we have a function that looks like this. I don't know what it does, but it goes back to the same height as it started. Then there has to be a point somewhere where the derivative is equal to 0. Now, do you see any resemblance between this statement and the mean value theorem? What was the mean value theorem again? It was a lot like that. Where what is 0? Right, so in the case of the mean value theorem, we would draw a line from here to here, right? And we would ask for a point that has slope or a tangent parallel to that line. But the slope of that line is 0, right? So Rolle's theorem is what we call a special case of the mean value theorem. It's a special case where the function, where the straight line L is actually horizontal. Okay? Then there exists a point C in AB such that, and this ST means such that f prime of C is equal to 0. Okay, now how do we prove that? What do you think? Yes?
F of B minus f of A over B minus A.
Okay, that's a good, so the suggestion here is f of B minus f of A over B minus A. That is correct, and if we had the mean value theorem, we can definitely plug that in, because f of B is equal to f of A, the right hand side will be equal to 0, and that will be a proof of this, right? Okay, but there's a problem with that. That's a very good point. So why would I be hesitant to use that argument? Once again, why would I be hesitant to use the formula f of B minus f of A divided by B minus A? Because it's what we're trying to prove. I'm going to the proof of the mean value theorem, so I cannot use the mean value theorem to prove it. Okay? No, I mean it's a valid point. I mean it's sometimes you think you already know something, so you use it, right? Yes.
Could you use intermediate value theorem on the derivative?
Yes. That's a good idea. Let's see. The thing is, you don't know anything about the derivative. But well, I think it's a great idea. The problem I would have there is that we don't know enough about the derivative. You say the derivative, the function is differentiable, and the function itself is continuous, but we don't know if the derivative is continuous, right? If the derivative is continuous, you can absolutely say that, okay? So then what?
You subtract f of a minus f of b, kind of find the midpoint, the average of the two endpoints, and then find the derivative.
Okay, you subtract f of b minus f of a. Right now f of b is equal to f of a. Okay, so any other ideas? No. All right. Let's see how much time we have. We're running out of time. Okay, let me just say this, okay? This is Rolle's theorem. This is apply Fermat's theorem to optimize mean and max of f. So for example, if the function, right, if the function has a maximum, let's say below f of a or f of b, right, then that point has to be a critical point. Okay, so for example, okay, I don't have time to write this down, but take the minimum of this function. The minimum has to exist, first of all, because we have a function defined on the interval from a to b, right? The minimum has to exist. Now, if the minimum is, let's say, less than this value, for example, if this value is, f of a is 5 and the minimum is 4, there has to be some point in between that has value 4. That point here has to be a critical point, and a derivative has to exist because you see the function is differentiable. Therefore, at that point, the derivative is 0. And that's the point we're looking for. Okay? Similarly, if there was a maximum that is other than f of a and f of b, say 6 instead of 5, that point has to be somewhere in here, some interval strictly between a and b. The derivative has to exist. So the derivative has to be equal to 0 because it's a critical point. Okay? Either way, if there is a point that is bigger than f of a or less than f of b, we have a point where the derivative is equal to 0. Okay? If none of those things happen, that means that the function is always exactly equal to f of a or f of b. In other words, the function is completely horizontal, in which case at every point the derivative is 0. Okay? So basically the proof of Rolle's theorem is an application of the optimization procedure we did before. And then we do exactly what Kendrick was saying. If you have a function that doesn't satisfy this property, that f of a is equal to f of b, then you rescale it. You subtract the function. You subtract, for example, this red line L, so that it does satisfy that f of a is equal to f of b. Okay? I'm sorry we ran out of time. Please take a look at the book for details on this proof. And we're going to move on next section next time.